This is our second video on circuits. Please write the notes down and then I'll move this up. Okay, you should have that written down. And then on the left side, here's a summary of series and parallel circuits. And then alright, just quickly let's go over this. A lot of this is review from last year. We did study power earlier in the year, and we said that power is a rate. It's the rate of doing work. And work is, according to the work energy theory, the work done, net work done, is equal to the change in kinetic energy. In this case, we are talking about the total work divided by, or change in energy divided by the amount of time it takes to change. And the unit for power is the watt. Remember, that's just a joule per second. Now, in electric circuits, we can take advantage of the definition of current and voltage. Current is charge per unit time, and voltage is potential energy per unit charge. And the product of those is energy per unit time. It's the rate of energy or the rate of work. And so power in electric circuits can be calculated using the product of current and voltage. If you apply Ohm's law to this, you can solve for power if you know one of these variables and the resistance, because we know that the Ohm's law relates the current and the voltage with the resistance. And you get two more forms of the equation, I squared R and V squared divided by R. Alright, you do need to know what a DC and an AC circuit is. DC circuits are circuits where the current goes in one direction, and those are the types of circuits you have when you use batteries or charge pumps. AC circuits, typically we think of those as the current moving through a circuit that is from a generator. We also have two types of circuits. We have series and parallel circuits. Series have one loop, parallel circuits have more than one loop. Remember, in a circuit you can have pieces of the circuit that are series. In other words, the elements are series. There's only one pathway for the current to go, and it has to go through all of the elements in the series. In a parallel circuit, the current goes into the parallel part, and then it has to choose a pathway. And then at some point, a junction, all the current comes back together and leaves the parallel part of the circuit. Okay, we have our summary over here of our characteristics of series and parallel circuits. This is just the resistance. To find the series resistance, equivalent resistance, you just add up the resistors if they're in series. And for parallel, it's a little more complicated. This is read as the reciprocal of the parallel resistance is equal to the sum of the reciprocals of each individual resistor. In capacitance, it's just the opposite. If you put capacitors in series, the reciprocal of the series capacitance is equal to the sum of the individual capacitors' reciprocals. And then parallel capacitors, you just add them up. Current in a series circuit is equal in all of the elements in the series. All the current has to go through all of the elements. In parallel, you have different pathways, and so you have to add up all the currents of all the different pathways, and that gives you the total current going through the parallel leg. Voltage is the opposite. For series circuits, the voltage across each individual resistor or element in series adds up to the total voltage, and in parallel the voltages across the parallel elements are all the same. Okay, we're going to be analyzing circuits, and there's a few steps. I've written just 3 here. We've practiced finding equivalent resistances in the past, and so the first thing you need to do is take your circuit and turn it into one equivalent resistor. You do that in steps by combining in series and parallel the elements. Then you solve for the current coming out of the voltage source, the battery, and then work back, adding elements until you get back to your original circuit. Here's an example that I worked out for you. It's a simple example, but it does show that here's 2 resistors in parallel, and these 2 parallel resistors are in series with this 5 ohm resistor. So the first thing that we do is we look for relationships. These 2 resistors have a common junction in to the parallel resistance and a common junction out of the parallel resistance. So they are in parallel. And we can combine those using the parallel resistance formula, and we get a parallel resistance of 5 ohms. So we replace this parallel resistance with an equivalent resistance of 5 ohms. Then we redraw the circuit, and we can then look for other ways to combine resistors, and I see that this 5 ohm and this 5 ohm are in series, and I know that because all of the current that goes through this 5 ohm has to go through this one, right? There's no other pathway, so it's one loop. And so we can add these in series, and the series resistance is just 5 ohm plus 5 ohm, which is 10 ohm. And so we redraw, combining these 2 resistors into one equivalent resistance, and that would be 10 ohm. And that's the final circuit. Now we can find the current coming out of the voltage source, and we do that using Ohm's law. So I coming out, I total is just V divided by R, 10 volts divided by 10 ohms, or 1 ampere. Now we go back and we apply that to the previous circuit, this intermediate circuit. So we're just going one step up from the equivalent circuit, the simplest circuit, and I see that the 1 amp has to go through the 5 ohm. There's no other pathway for it. So I know that 1 amp of current goes to this 5 ohm resistor, so I can figure out the voltage of that 5 ohm resistor using Ohm's law. V equals I times R, so V equals 5 volts. 5 volts is dropped across this resistor. Now, if 5 volts is dropped across this resistor, then we know that voltages in series, and I can pull back up here to this summary, voltages in series add up to the total voltage. The total voltage is 10 volts. If I drop 5 across this 5 ohm, then I drop 5 across this parallel resistance. So I've written that here. 10 ohm is equal to, 10 volts is equal to 10 volts minus the voltage of the 10 ohm resistors is equal to 10 volts minus 5 volts, which is equal to 5 volts. Now, this might be confusing to you. I wrote this because this parallel resistance represents 2 10 ohm resistors in parallel. This voltage is whatever is across these 2 resistors. Whatever they may be, their equivalent resistance is 5 ohms. And probably, maybe I should have written this as 5 ohm equivalent. Anyway, now that I know the voltage that goes across here, I know that that same voltage is across both of these 10 ohm resistors. So there are 5 volts across both of these 10 ohm resistors. And I can then figure out the current going through each one. The current through each one is just V divided by R. So we have 5 volts divided by 10 ohm. Okay, so that is an example of circuit analysis for a simple circuit. And let me flip over. I've got one more thing that I want you to record in your notebooks. This is some additional tools, and so you're going to write these on the next right side of your notebook, and we will talk about these in class. And here is some examples that we'll go over in class.